Look at this structure. It's a massive, multi-ringed natural product. Try to describe this exact shape to someone over the phone using only everyday words. You'd quickly run out of ways to explain which carbon points up, which branch loops back, and where every specific oxygen atom sits in three-dimensional space. Yet a chemist can transmit the precise blueprint for this exact molecule using a single string of text, a seemingly incomprehensible block of letters, numbers, and brackets that contains every piece of spatial data required to rebuild the entire architecture from scratch. The IUPAC system functions as a strict logical algorithm, a high-efficiency data compression protocol designed to parse chemical structures into text. Underneath these names is a universal formula, a modular syntax of 6 distinct blocks. Each block serves a strict function. The root tells the total carbon count. The suffixes declare priority functional groups and saturation. The infix maps ring structures. The prefix logs side branches. And the stereo block locks in exact 3D orientation. By feeding a molecule through this sequence like a logic gate, we can systematically deconstruct any organic compound, no matter its scale, and generate a completely unambiguous name. The algorithm always starts by establishing a backbone. When you look at a branched carbon structure, the first rule is to trace the longest possible continuous chain of carbon atoms. That path becomes your root word, like hex for 6 carbons, or oct for 8. But organic chemistry is rarely just straight carbon. Let's add an alcohol group, an OH, and a carbon-carbon double bond to the same molecule. Suddenly, figuring out where to start counting isn't so obvious. To resolve this, IUPAC uses a rigid hierarchy. This text block from the official rules dictates the order of precedence for functional groups. The group sitting highest on this list is crowned the principal functional group, and it dictates the entire identity of the molecule. Scanning the list, we see the OH group outranks the carbon double bond. The alcohol wins. This victory triggers the golden rule of numbering. You must number the carbon chain starting from the end that gives this principal functional group the lowest possible number. It pulls the entire numbering system toward itself. Because the alcohol won, it locks in the secondary suffix at the very end of our name. We append all. The lower priority double bond doesn't get ignored. It controls the primary suffix, sitting just before the alcohol, shifting our ane to an ene to indicate the chain is unsaturated. Identifying this highest priority group is the critical anchor point. It orientates the skeleton and defines the molecule's chemical family long before we even look at the side branches. Now we map the remaining atoms, the halogens and extra alkyl groups hanging off our main root. These side branches serve as the prefixes in our formula. We identify what they are and tag them with the exact carbon number, or locant, where they attach to the backbone. But we don't list them numerically. The algorithm forces us to sort them strictly alphabetically. Chloro comes before ethyl, which comes before methyl, regardless of their locant numbers on the chain. If we have multiple identical groups, say 2 methyls, we use a multiplier prefix, making it dimethyl. But the algorithm ignores this multiplier during the linguistic sorting. Dimethyl is still alphabetized under M, not D. Ignoring these numerical multipliers during alphabetization prevents competing interpretations. It ensures that 10 different chemists analyzing the same structure will all compile the exact same predictable sequence of text. Flat chains are relatively simple, but the algorithm has to adapt when carbon skeletons warp into closed loops. When multiple rings fuse together, we activate the infix step. Take a look at this structural diagram. This is a bicyclic system, defined by 2 rings sharing multiple carbon atoms, known as bridgeheads. To number this topology, the path must begin at a bridgehead. From there, you trace along the longest possible bridge to the second bridgehead, then the next longest, continuing in strictly descending order of bridge length. That pathway generates the bracketed numbers in a name like bicyclo-2,2,1-heptane. Now compare that to a spiro compound. As shown in this example, spiro rings share only one single intersecting carbon atom. Because the topology is different, the algorithm inverses its logic. You start adjacent to the spirocarbon and trace around the smaller ring first, ascending in size. These opposing rules act as topological wayfinding systems. They ensure the counting mechanism never overlaps or maps identical atoms twice when navigating complex fused geometries. Everything we've mapped so far exists in 2D topology, but atoms occupy 3D space, and right-handed and left-handed variations of a molecule can have vastly different chemical properties. To encode chirality, we use the Can-Ingold prelog priority system. This rule states that the groups attached to a chiral carbon are ranked strictly by atomic number. Oxygen beats carbon, carbon beats hydrogen. Once ranked, visualize the molecule in space. The lowest priority group must be rotated away from the viewer, pushing it directly to the back. With the smallest group hidden, you trace an arc through the remaining 3 groups, from priority 1 to 2 to 3. A clockwise arc assigns the prefix R for rectus. Counterclockwise is S for sinister. A similar logic applies to the rigid geometry of double bonds. This visual shows the EZ notation system, where we split the double bond in half and apply those exact same atomic priorities to the groups on each side. If the highest priority groups on both carbons sit on the same side of the bond, the prefix is Z for zusammen. If they sit on opposite sides, the prefix is E for entgegen. These stereochemical prefixes lock in the final spatial coordinates. They allow a chemist to pull absolute 3-dimensional reality right off a flat piece of paper. Let's put the entire algorithm to work on a master structure. First, we scan for the principal functional group. It establishes our numbering priority and drops down to anchor the name with our root and suffixes. Next, we map the backbone. Tracing the fused bridgeheads using the descending logic of bicyclic topologies gives us our structural infix. Then, we catalog the remaining side branches, applying multiplier prefixes where needed, and slotting them into a strictly alphabetized list. Finally, we determine the atomic priorities around the chiral centers, assigning their spatial coordinates and placing them at the very front of the chain. The IUPAC name is executable code. It provides a precise sequence of grammatical rules that allows a chemist to perfectly reconstruct complex molecular architecture.